for having me here. I think we move a bit away from foundations of zero knowledge proofs and snarks into applications. I'm here for that. And let's see a bit what snarks background we saw so far. So just the definition of snarks. In terms of their properties, they are succinct. This means that the proof size is independent of the witness we want to prove, non-interactive. This is for the N. Then there are arguments in the sense that the soundness is only against computationally bounded provers. And they are knowledge sound in the sense that we can efficiently extract the witness from the prover. So this proves that we have knowledge of some witness. And of course, as we saw, usually we construct such a snark and then we kind of use some randomness or some hiding in order to add zero knowledge to it. So this is optional, and as in previous talks, I will probably skip anything that is zero knowledge from the presentation. I will focus on the succinctness. Okay, so building snarks follows these steps. We saw it this morning. We have to start with a target statement that is in general a computer program or anything very generic. And in order to compile it into something that is useful for cryptographic purposes, we need to first write it in an arithmetic form. And this is using this arithmetic circuit satisfiability problem, which is NP complete. So hopefully any problem can be written as an arithmetic circuit over a field. And that's great because this allows us to talk about polynomials. So we saw how we go from a circuit into a computational model that is friendly for processing and compiling it with cryptography using polynomial commitments, notably into a snark. Okay, so there were many schemes, like this is not an exhaustive timeline of snarks, but there are many schemes that were discussed here and some schemes that I want to mention. So I will divide them into three areas, like it was this incipient beginnings of zero knowledge proofs, which is more like a theoretical approach and some construction for specific relations, like sigma protocols that don't prove generic computation, but something very specific. And then there is the modern era of snarks, where we started constructing things based on pairings and more sophisticated assumptions. And this lead to the non-interactive ZK proofs that don't need Fiat-Shamir transform. And of course, we introduced this common reference string model where we have a setup that we rely on for building the snark. And more recently, we have this practical era of snarks where we really design schemes that are optimal for the proof size and the verifier runtime, and these are based still on pairings. They have this trusted setup sometimes. Then there is the bulletproofs, which is more it's prover efficient and has a verifier linear, and we saw it this morning. And then there is this universal setup that mostly rely on KZG polynomial commitments. Okay.
So is GGPR, is that Pinocchio?
Yes, or before Pinocchio, it was the one that introduced QAP, quadratic arithmetic program, as a characterization for NP. And then these ones use something equivalent with QAP, which is R1CS that Carla introduced.
Sorry, what do you mean by no PCP?
No probabilistic computational proofs, which were used before to construct succinct arguments. Yeah. With hash functions and different techniques. Okay. So we are focusing on this last part, the recent snark research, and even further. Let's consider that we have the schemes, which is true, and even like that, we find some challenges in using them in actual system because not everything scales very well with our applications. So because of that, there are some techniques today that I will talk about that allow to scale even more already very efficient schemes. So these are aggregations. So we will aggregate multiple snarks into shorter proofs. Then recursion, I will mention it briefly, lookups, and folding. I will touch more on aggregation, recursion, and folding. Okay, those are just for the references. Let's see application that motivate usage of snarks and why we need to even scale them even more. So your favorite application, cryptocurrencies, love it or hate it, but I actually look at cryptocurrencies and blockchain as a resource for so many interesting open questions on snarks and zero knowledge proofs that allow the field to develop very fast and at a pace that we see today with a lot of papers coming out. So just a brief description, like very simplified description of how cryptocurrencies work, so we understand where the snark plays a role here. Like these are distributed ledger, which are public registers of all the balances of the people who are in the system, of the users, and they have some public keys. So these names here hold for some public key for these users. And each user has their secret key in order to perform transactions. And in order to move coins from one user to another, that user should upload in the blockchain this transaction where they demonstrate they have the balance, the required coins. They are themselves, so they sign this transaction with their secret key associated with this public key from here, and the amount that they want to transmit to both. And what's interesting about this is like the blockchain is like a ledger, a public ledger that keeps track of all the transactions. So it's a list of what happens there. So somebody has to come and check and change what the state was from before, and the transaction is validated and it's performed only if some validators or some other peers in the network come and check that this was valid with respect to the secret key, like this is a valid signature and the coins correspond with the balances. And everything is public. Everything can be validated by anyone who can just download the previous state, and then some consensus is needed to come with a new state. Okay, so some important properties is like this gives some inclusive accountability. Anyone can see, as I said, and check actions that happen on blockchain. All the transactions are public in this model I show. And because we need some consensus to decide which is the new state, like we need multiple nodes to check the new blocks. Okay, so I want to emphasize where snarks and zero knowledge proofs in general are useful and are used in these systems. And here are properties and some systems that use snarks for the zero knowledge property, for the privacy. So as I said, everything was public in a regular cryptocurrency blockchain, but we can have cryptocurrency that guarantee privacy of the transaction, TX is for the transaction, on some public ledger. The ledger is still public, but we don't know exactly which user transferred coins to another, and this is done by just validating proofs. So the proof will look like I have a secret key that allows me to do this transaction, and my balance allows me to transfer the money. Okay, and that's enough to keep privacy for everyone and to make sure that everything happens as expected. And the zero knowledge proof doesn't reveal more than that, as I said. And these are kind of some example of systems that use them. And then we have compliance. And this is another application that, for example, this company, Espresso System, uses zero knowledge from snarks to prove that the private transaction is compliant with some banking laws. So, for example, that an exchange is solvent, but also they protect the customer's private data while doing so. So this is why zero knowledge is important. Okay. And now we have zero knowledge proofs using distributed system, but for the proof size. We don't really care about privacy or hiding anything about the winners, but it's just we want to prove things in a more efficient way than just showing a long computation. So as an example, there is Filecoin blockchain and a system that is a peer-to-peer network for storage. And this means that anyone in this network can make available some storage space on their computer and store files for other people in the network. this is, of course, is not a trust network, so we need to guarantee that we store files. Any user here storing files, like a storage provider, should prove that they still have the file of the users. And that's done by periodically posting snarks that allow to check that the file is stored permanently. And of course, they earn some incentive to store the file, so they need to prove in order to be rewarded afterwards. And curiously, this is the system that deploys the most snarks in practice these days, and it's like kind of 6 million snarks posted on their blockchain every day. 6 million snarks computed, and we'll see how they're posted. Okay. And there are other things that we can do with the proofs from zero knowledge snarks. Bridging blockchains. So two different blockchains do not communicate with each other. And the way to move assets from one blockchain to another will be to make a proof to the new chain, to the chain on the right here, that some assets were locked in the other chain until like the consensus is that those assets should be moved on the other chain, and this chain should believe that and accept them, and this is how we bridge two chains. And of course, it's needed to have proof of knowledge that what happened in the previous chain. Okay. And we have a very nice and interesting scaling application. So I was saying that this transaction should be checked for by everyone, and this costs what we call gas in blockchains. Like, it's expensive. Somebody has to pay for those who validate the transactions. So any transaction will cost money somehow. A way to do it cheaper and faster is to outsource the validation of transaction from the main chain here into some service that will do it for the users. And outsourcing means that somebody else will check that transactions are valid and not post them all, but post a proof that the checks were correct, and this is the new state, right? And this we call layer 2. And this is reducing the cost in terms of validators' time and effort of the transactions. Of course, there's no need of zero knowledge because the transaction will be public anyway, but there are applications that use zero knowledge also for that, to also have privacy and scaling in the same time. But we need succinctness, which is important for this, and proof of knowledge. Okay, and I have a lot of examples of systems that use this in practice, but I will add them in the slide after when I publish this. So the new requirements that come from this application in blockchain are that the proofs should be non-interactive, because, as I say, this is a distributed setting where anyone in the network can come and check things on the blockchain. So it should not be designated verifier, or the verifier should not need some secret state. So this is publicly verifiable, non-interactive, and we need succinctness, which is very important because blockchain are kind of like, you should think about them as a very limited computer where we don't have a lot of memory, we don't have space, we don't have a lot of computational resources, because those are costly. Somebody has to check things, and blockchain are like limited in terms of bandwidth. And we need efficiency for verifier, of course. But we also think about the scaling because of the prover effort. So we'll see that in a minute. So the answer to this actually are the snarks we saw before, the succinct non-interactive arguments of knowledge. And if we need privacy, we can add zero knowledge, as we say. So it seems like the problem is solved. We can use them, they are used already. And what can we hope for more? So what is left to do? So what is left to do is like the scaling problem I was mentioning, and that's what is called ZK rollups, which is misnamed ZK without caring about zero knowledge too much. So I was saying, like, these blocks have a lot of things to be published on and to be verified, so they are deferred to some second layer, to some outsourced service that will do the transaction check and will post on the chain only the result of that, of the change of the balances, and approve that that was done correctly. So let's see a more concrete thing. The statement will be that the state, like this, all this transaction will be run on a parallel blockchain that is not public, is not the main one. And we will look at the transaction, we will validate it, we will upload the new balance and then continue doing that. But as a parallel, like a side chain when this happens, and only a proof that the state changes correctly from state 1 here to state 3, and everything was validated correctly in order to have a state 3 right now. The state is correct, and this is a result of the execution of some transactions. Okay. So how we will do that? So if we have a bunch of transactions that we need to prove in some way, we realize that kind of proving them all, wait all the transaction, checking them, and at the end have this transcript that is our witness of what happened from one balance to the other, and proving them at the final moment before putting them on the main chain takes a lot of time. So proving becomes a problem when we have big circuits to prove. And we should find a better way. Either we should improve the prover performance, either maybe do it sequentially, and this is kind of like the idea. Let's do it by periodically proving something. So we batch transaction in each block, like these blocks parallel, and we prove each block separately. So we batch them into multiple bunches of them. And then we send all these proofs to the main chain to prove that from state 1 to state 3, all these changes happened. But this makes the verifier slow, right? We need to check a lot of proofs, and this will slow the process of validating what happened in the last block here. So it's not quite a solution. So the question will be, how do we do it? How do we prove things that happen off-chain, and how we scale those proofs to make them published and verified fast on the main chain? And also remember that there is a like size problem. We cannot publish so many things in a block. It's like limited size. Okay. So let's see in brief the kind of some ideas to solve this. So if we have multiple instances to prove, we can take them separately in a naive approach and prove them separately, but like even one by one, and then inspect them one by one. So this means verification is very, very long, but instead what happened in the beginnings was, yeah, we have a lot of proofs, but we can batch the verification if the proofs have some algebraic structure, which is nice because the verifier is slow, is faster, but we still need to publish many proofs. It's still not out. So a new approach will be to aggregate this proof. Like we have proofs and we can aggregate them together into something shorter that if this is valid and verified, this will imply that all the initial proofs are verified. We can do the aggregation. So this has a fast verifier, and the advantage that the aggregated proof is so much shorter than the initial ones. And then we can do recursion. Recursion is a way to, we already saw it in the lightning talks, and Carla mentioned, it's a way to add to the proof. So we first prove something, and then we have to prove a new transaction. So on add it, instead of retaking two transactions from, we have already a proof for the first one. So we add to this proof the new transaction, and we prove that this was a valid proof. The initial one was valid. So in some way, we prove that the verification algorithm for this proof output 1, accepted the proof. And so on at each statement that comes in the system. This we can do sequentially, so we don't have to wait till the end. But as you can imagine, these proofs like come with some complexity. The recursion is not very easy to realize, and we will discuss a bit how. Another way is to do folding. So folding means the folding techniques look at all the witness and statement to be proven, and wait without proving, but just fold them. And at each step, a new statement comes, fold it with the old one, and obtain, without doing any proof, obtain a very short statement that only has the size of the first one. one is single statement. At the end, we will have all this folded statement that was folded step by step, and we can only perform the proving once. Remark in these techniques, like if somebody else needs to prove before and we come later, we cannot do it. We need to have all the statements and to know the witness.
Anca,
Yes.
one thing is that maybe because it's confusing, that folding is used often in the context of recursive proofs. So here is like a bit of a different
Yeah.
meaning than the usual one, so that it's maybe
Yeah.
good to clarify.
I make a difference between atomic accumulation, split accumulation and atomic.
No, but just mean because they use it.
Oh, they use
only
it as a
for
name.
for
Oh,
recursive,
yeah.
in the recursive composition.
Okay. Yeah, like the term folding as I use it is a bit different from how literature may use it in the recursive. Yeah, that's true.
Just another small remark. Basically, with like one naive way to do this would just be to take the end of all the statements, but of course that's not how it's done. Like then the size of the statements blows up if we just combine all the statements into like the logical end of all of them. Yeah.
Yeah, this is
So
what
that's like you need.
we wanted to avoid,
Yeah.
to have to prove a big circuit that models all the computation and want to kind of divide it into smaller steps or fold it before we prove it, or yeah, like different techniques how to deal with very big and many statements to prove in some way.
Yeah, I want to understand the discussion with Carla. So you could use a folding scheme where the verifier kind of has all the instances and folds the instances, but that would mean that his work is linear in the number of instances that are being folded. And it would work with a folding scheme, but it's not what the guys that do recursion using folding do. Is that what their
Yes.
point?
Yes,
Mhm.
that she means that, not what exactly.
Yeah, exactly. Like here it's the verifier and the prover first fold and then only once prove, yeah. Okay, and this is a bit of a comparison between the three approaches. So proof size wise, they are kind of comparable. Maybe recursion can have a bit more. The verifier time, of course, it's longer in recursion, but we will see some techniques that makes it improves it by amortization. And the prover time, of course, is the worst when we first prove individual statements and then we have to do another work to aggregate them. That's an additional work for the prover. Okay. So let's start with the snark aggregation, the first I was mentioning, which is this one, and see how we construct such a scheme based on, and this is like the summary of how it works. And we will do it based on Grot 16 scheme, but let's first motivate it by this distributed storage example that I was giving. So here in this network of peer-to-peer storage, as I said, we have provers, which are the storage providers, the one that want to show to the network that they regularly they store they put storage capacity for everyone, and they have to prove it. And anyone in the network, the verifiers can check that those proofs are valid. So the problem is that if you want to upload storage to the network, you have to prove that this storage, you have this storage and you maintain it with the time. So we need to do a very large proof of some large computation. And how it works, for each 32 gigabytes of storage, which is a unit in the system, you need 10 snarks to prove that you uploaded in the system. So imagine for someone who wants to upload like 1 terabyte or something big, you need to submit all these snarks on a chain, and this like kind of the chain is limited into how many proofs can be uploaded. So this sets a limit on how many people can adopt the system, which is not what the intended system was at the beginning. So a way to avoid this is to have like a node that aggregates proofs, either the original storage provider or a node that takes these proofs, and instead of putting them on chain as many as we have, we aggregate them first. The size of the resulting aggregated proof is just logarithmic in terms of how many inputs, how many proofs we aggregated, and only publish this. And the verification will also be like logarithm. So this is a prover overhead, but at the cost of a prover overhead, we have shorter proofs and faster verify. Okay. And we will do so for growth 16 proofs for the same relation. So as we saw this morning, growth 16 proofs, we don't need to know more than like this kind of toy representation of a growth 16 proof. Growth 16 proof have structure reference string. So this is a trusted setup that is depends on the relation to proof. And in our case, we will luckily have the same relation for each proofs. So all the proofs are run for the same relation. And a proof is 3 group elements in this bilinear group that look like this, A, B, C. I put them in yellow if they are in the first group, and this orange is for the second group element. And the pairing, it's a bilinear pairing, like the pairing check at the end, it's not the one in the paper, but it's sufficient to illustrate how it works. So here is a pairing between 2 elements of the proof, and here is another pairing to check on the third element with some D that contains the inputs. Like the verifier also has to compute something depending on the inputs. This is what D will hold for. So this is our pairing bilinear proof groups and pairing notation in additive notation. The one with brackets 1 is from the first group, brackets 2 is for the second group, and this is a typo. Should be 2, and this is a target group. Okay, so the pairing as Arancha presented allows us to just check quadratic equation in elements encoded in the groups, in the first and second group, without computing the product, just checking if some 2 products are the same. Okay. So if we have many snarks, the verifier will compute some D, which is like a discrete log or some small d, and have to input, let's pretend D is the same for all. It's not the case, but for the purposes of illustration. And we have to check all these pairings. Like in a naive approach, we will take it one by one and we will check them. But we already have a method to check many pairings from growth 16 verification by using batch verification. This doesn't save us on proof size, but the verification time can be improved by doing them all at once. And how does it work? If I have so many equations to check, instead of looking at each of them, I will just batch them by sampling a random element and computing a random linear combination of each of these equations and check the random linear equation. Right, so I will check that the sum of randomized first one plus second one plus last one is equal to the sum of the same randomization on the right side. And this should, because R is picked at random and independent of this equation, should convince me that if this holds for random R, then each of the individual one with high probability also hold.
Maybe just for context, right? Like what you're saving here is the final exponentiation of the after the pairing, right?
Yes,
Final
but also,
exponentiation in the target.
also doing each pairing separately, because you will have a final exponentiation everywhere, right? If you look at them as separate entities.
Okay.
Here we'll do a multi-ex.
Also, I think actually it would make more sense if you were putting the RI in the pairing in the D.
Yeah, I will do that in one. Yeah,
It's the only one. You're saving
Yeah,
that
yeah,
pairing.
I want
Wait,
it.
but you're still doing the pairings, right? It's just the final
In
exponentiation.
this case, for the second argument, no, because the D is the same.
Oh, for the D. Okay, yeah.
Okay, there was one more question.
Could you please go back one slide?
Yeah.
Maybe one more slide.
Okay.
I guess one more slide, please. Here, I'm just wondering if you could confirm, the implication is that AI is a different proof than BI is a different proof than CI, like a different collection of snarks?
Exactly. Yeah,
Okay.
it's this
Just checking.
one proof is 3 elements. So here I have n proofs.
Okay.
Yes. Yeah. And each proof needs to have an equation of its own.
But in that case, in that case, is the implication that you're using bilinear pairings in order to have one of the proofs in the target group?
The bilinear pairing is used only to check that the relation between these group elements holds, and that validates a growth 16.
The AI, BI, CI are just 3 elements in one proof.
Mhm.
And then for each of these equations there, that's just n different proofs.
Yeah, the verifier should check that some equation holds between A, B, and C from each group.
By exploiting some like relationship between them?
Yes, like if the prover had the witness, those will satisfy some quadratic equation.
Got it, okay.
They're encoding of some polynomials that it's very related with what we saw before, like they should be some polynomial evaluation, some points that have a relation between each other. So I skip that because it's not important for the aggregation. Okay, so as Carla saw, if we look at the properties of bilinear groups, we can easily do the linearity of the and we'll have here the sum of the randomized CIs. Okay. And we have to check that some of pairings here on the left is some unique pairing, but with this element. So the idea behind snark packing all this together is to ask the prover to do the batching and to prove to the verifier they did it correctly. So instead of the verifier to receive all the separate proofs and do this, they will receive only the things that they need to check. So they will receive the left side term here, which is ZAB in my notations, and they will receive the right hand side term, which is ZC, only this one, and D should be computed by the verifier. Okay, so defer all the computation of this to the prover. And the verifier will just have to check an equation given some elements from the prover. But we are not able to trust that the prover will do the correct computation. So we kind of need to prove that ZAB is what is claimed to be, and ZC is what is claimed to be, given some initial proofs and proofs, right? So that's what aggregation scheme will do, actually. So the starting point to prove this relation between ZAB and ZC are proof of inner pairing products and application by the Smaller and all, which show how to prove generalization of inner products. So we saw bullet proofs this morning, which proves inner products over field elements. And here we have vectors of group elements. Remember that the proof elements AI and BI belong to some groups in the bilinear group we have. So what does it mean to prove like an inner product over a group element and a field element? It's actually the sum of RI AI. It's defined like that as a generalization. And it looked like a commitment, if you remember from this morning, commitment which uses a base as a group element. Like this vector AI can be like a base, and this is a commitment to RIs. And on the other side, what does it mean to define an inner product between two group elements, group vectors? This means that we just define it in terms of pairing. So we have, instead of a product, because we don't know how to make the product, we'll compute the pairing between AI and BI and sum these pairings. And this is the generalization of, and to see it appear as an actual inner product, you just write it in the target group element here. And you will have appearing sum of AI BI, which is exactly the inner product we know from field arithmetics. Okay. And same if we write it here as elements from group I, and these are the discrete log of each AI. Okay. Okay, so using these tools, we know we have something that allows us to prove this kind of generalized inner products, and we call it multi-exponentiation inner product and target group inner product. And let's get back to our proof. So our proof asks us to make a linear combination of the elements. So we put them in this ZC and ZAB. And if we look closer, they look exactly like that. Here should be additive notation, so R is here, like here. And we just need to use MIPP for the first check and TIPP for the second one. Those run in logarithmic type. So let's see a bit the strategy, even if we saw it this morning, to see how useful these tools are that Carla presented as the foundations, and they are used in different settings, like this in target group elements. So what I call it is split and collapse, or split and combine, as we saw it. We take a long statement, this AB inner product, and we have two vectors of size n for which we want to prove that this holds. And what we will do, we will cut them in two halves. And we will kind of compute this overrun here. We will kind of compute some new vectors, A prime and B prime, which is of size half A and B. That is a combination of B left and B right here, for example. So from these new vectors, we will define what is A prime, B prime, a new inner product. And we will see what's the relation between the new inner product and the original one we wanted to prove. Okay. So the relation is in terms of cross terms, as we saw also for bullet proofs. So the new Z prime AB, which is a new claim inner product for half and half B, is the old one plus some left cross term plus some right cross term, which left is the right left kind of, and right is the left part of A and right part of B. It's kind of intuitive, non-intuitive. I should call them right, left, and left, right. So, yeah. So if we recurse on this, now we have to prove a new inner product between a vector of half size here. And the new vectors are some collapsing, some combination between A left and A right, this A half and B half. Okay. So for the verification, as we saw in bullet proofs, normally this will result in a proof of logarithmic size for such an inner product. Let's take this one only. And because we halve the vector at each time, but we need to commit to it, we have to halve the commitment key vector as well at each side. And this was taking linear time for the verifier, which was something that we want to avoid because we wanted to aggregate things and to have a faster verifier. So an idea to overcome this is, of course, to use structured trusted setup. So if we have the usual structure that we saw in KZG, like powers of some tau, powers meaning like they are encoded in the group one and group second group, then we can commit to these vectors using this structured commitment key, and checking the commitment key at the end will be sublinear, will be logarithmic. So let's just briefly recall what we saw already about, I will call them vector commitment because I don't have polynomials here. So we have a commitment key. To commit to a vector, we still write it as a polynomial because this is the tools we have. And we do the KZG commitment as we know. We evaluate this. And there is a new commitment I wanted to present, which is the target group commitment that we will use for group elements here. So we have group elements from A1 to AN. Okay. And those can be committed by using the pairing and the same commitment key. Actually, we will use the same commitment key, but in the second group, of course, if we put it in the second place here. So to commit to group elements from the first group, we will need the same key, but in the second group. And we will just define the commitment like this, and we can prove that this is binding and has the right properties. Okay, so that's the commitment. And why do we care? We care about the commitment and having a structure key because, as I was saying, we need to care about the split and collapsing of the key from the verifier. At each step, at each round of the protocol, you will receive an alpha challenge, and you will have to split the key until you will have a key of one element. And as Carla presented, we can express this the formula for the last key as a polynomial in terms of some variable x with the coefficients defined by alpha, the challenges we receive, and alpha has as many as the rounds. Okay. So we have the linear verification because of this polynomial can be reduced to logarithmic because we have only logarithmic number. The verifier knows all the challenges, so can compute this and can ask the prover to open the polynomial in some secret point. Like that, we can check it in logarithmic time. So that's the trick to have sublinear verification. And let's see the actual performance. So if we look at the aggregation, what the prover should do is to really do the commitment to A and B, which is this pairing. Like commitment A and B can be done in the same commitment, but it's a it's a lot of pairings to compute in the target group, and same commitment C. And then we need to generate the logarithmic proofs MIPP and TIPP, which is each linear in the size of those, but the proof has logarithmic size. So the prover, the overtime for aggregation, it grows with the number of proof we want to aggregate, but because we can parallelize it, it's not that bad. So 2 to the 70 proofs is quite a big amount of proofs. We can aggregate together in 2 minutes, which is quite good if we save on verification and size.
It goes linearly, right? Well, it looks bad, but it's just linear growth.
Yes. Actually, we have to do all these pairings here. Yes, it should go linearly normally, but I think parallelization. Yeah, I don't know why it looks like that.
Exponential x-axis.
Yeah. The time kind of grows a lot after we have a lot of pairings to compute. Yes.
So this aggregation works if you replace C times R with D times R, right? Does it like improve concrete efficiency, or it doesn't matter much?
This one? Yeah, of course, because here we don't want to compute pairings. We just compute multi-exponentiation for C, and here we need to compute pairings of A and B.
Well, you can do D times R instead.
This one?
No, the MIPP.
Oh, yeah.
So this could be just an
Oh,
of D's and then times R.
oh, I see. No, you need C from the proof, right? Maybe I don't get your point.
Was D
The D was an input from the verifier.
okay.
It was computed for the verifier, so it has nothing to do with what the prover should send. Yeah. We need to randomize all the C's with the same RIs that we use here.
So sorry, for randomizing, what is the security? I mean, the sum is lost in these terms. I suppose that's not going to be realistic, like checking all the proofs individually. And now there is a chance that maybe all of them are going to be fulfilled. However, it's not the case for each of them.
So one implication is always true. Like if the initial one are fulfilled, then of course, when you randomize, the final equation will also be fulfilled. The other one, indeed, relies on the fact that R is at random and independent
From
of
a huge distribution.
and independent of the number of proofs, like of the proof values.
Look at it basically as a polynomial equation, and the degree of this polynomial is basically how many proofs we are aggregating, and then you have this divided by the field size, or
You can use like Schwarz-Zipper, like using the degree of a polynomial in R, because we use powers of R actually, not RE that way. Okay, so the aggregation, the proof size. So the proof size is quite nice because of course with batching, we didn't save anything, we just sent all the proofs. So this is logarithmic. So for very, like for many proofs, it's kind of not growing. Okay, and also the proofs are, the resulting aggregating proofs are in target group as elements. So we use a lot of like improved ways and compressed way to represent such target group elements. Okay. And for the verification, like as I was saying, there is a logarithmic n proof to check with all the MIPP and TIPP rounds, which are logarithmic size. We need to check the CK final, which is logarithmic time, because we need to compute a polynomial of log time with log time variables that are allowed to compute it. And only one pairing check at the end. Okay. So the verification really saves a lot, because before batch verification means that we still have to do all the work that the prover did now, put together all these proofs with a randomness and then batch verify them. Here we just receive them and we verify them. So we can do 8,000 proofs in 33 milliseconds, which is kind of impressive. Okay, so that,
Is deployed on
yes,
the pipeline?
yeah,
Okay.
yeah.
A quick question. What changes when you have different public inputs to like each of the proofs? Like,
Oh, it changes how the verifier computes each D. Each equation will have a different D.
Yeah.
So that's something that is inherited because the verifier needs, the verifier needs to check the inputs. Like a proof without any statement doesn't mean anything. So, and here it's not like a recurse computation where the input or the output of one previous thing is the input of the second. They're quite independent. So you really need to read the input.
but it computes like some structure preserving commitments to like all of the individual DIs manually, or it do something smarter?
Individual, sorry, I didn't.
Like you will have different Ds. So
Oh, these yes, these are should be computed by the verifier.
Yeah, yeah.
Yeah, and they are group elements that come from some input, which are the fit, like the X size you get in the computation or something.
okay, yeah.
Yeah.
And then you're changing your inner product with like how do you feed these Ds into this argument?
Oh, you just put it in the pairing afterwards, like
Okay,
it's a D final that
Ah.
resulted from many different Ds. But in my example, all the Ds were the same, so it's very easy to present. Yeah, but in real life, this D is also randomization of D1 plus randomization of D2.
Okay,
It's the sum of, and that's still the verifier's work to do.
yeah, no, exactly.
Yeah. Okay, yeah, that's a good question. Yeah. So yeah, of course, the real protocol looks more ugly, but I hope the idea. Okay, so let's go to, in the last minutes, I will try to briefly present snark recursion and like the main challenges for snark recursion and snark folding. So the recursion means that I want to prove, like I will call inner snark the snark that just proves a circuit, a relation that is a circuit with the witness and of course the inputs. And we have a verifier for this snark that can check that the proofs is valid. And recursing on this means that I want to make a proof of this proof, that this proof is valid. So now the witness will be my already generated proof. And the secret I want to prove in the new snark, in the outer snark, is the verifier secret for this inner snark, right? Makes sense? So what the prover will do, we'll have a proof pi prime that says that pi satisfies the verifier secret from here. Okay. So this looks quite nice if we can do it, and why we will use it. So for example, instead of aggregation, if we have many proofs here, if we have recursion, if we can prove the validity of another proof, we will just make a final proof of proofs that says all of these are verified. So this of course will incur a lot of delay for the prover because you need to prove as many statements as the number of initial proofs. So maybe it's not the right use case, but just the better use case that we also saw in some Lightning talks is to increment the computation at each step and prove it at each step. So the recursion on incremental verifier computation is like we prove something and then we add some computation. Usually the output of this is the input of this. And we prove the new value and the fact that we already proved the old thing. So this is how we use it, and this is what incremental verifier computation does. We recursively apply some function on the output of the same function, and we obtain new values. And this is some other state input here. And if we want to prove such a sequence of computations, this will look like this. We start with no proof, with just an input and this t input, and we run the function and the verifier secret. It's always this, but here we don't have proofs. So on the second step, we have one proof that the function was applied correctly once. So we need to apply the function again on S1, have S2, and verify that P1 was correct with respect to this proving system. So this is how we can use the recursion. And now, why is challenging to construct such things? Let's imagine the scenario where the verification runtime is linear in the circuit size for the snark. So as it is in bulletproofs. So in bulletproof, verification is linear in the computation. So if we have such a situation, let's say 2 is the constant, we have 2 times the circuit size. First, we have to prove the circuit, and then the verification for this proof that we have here in the first box will run in times 2 times the circuit, right? What happened with the verification for this already generated proof? This will run in 2 times the secret from before, which is the verifying secret for the first proof, which we decided that is 2 to the secret, so it's 2 to the power 2 secret. So at each step, it increases exponentially in the size of the secret. This constant will blow up, right? So that makes us conclude somehow that we need sublinear verification in order to be able to construct such a recursive thing. It's kind of inherited. Another thing that we should take care about is that the verification should be arithmetized in order to be able to feed it to the prover as an arithmetic circuit. And in general, it's not a computation that looks exactly as what the prover was initially designed for. So for example, in the Growth 16 example where we have sublinear verification, we have constant size verification, the verifier looks like check some curves operations, check some pairings on a curve. So if we have a pi1 here for a secret that works over a field of size q, which is a prover that can generate elements from an elliptic curve that has order q. So this is our group. It's an elliptic curve defined over some fp. We don't know what p is best, but we know that this elliptic curve has order q, so we can work with field elements of scalars of size q here. So if we have this, the verification will have some operation over this curve, and this curve, as I said, is defined with points over some field fp that has nothing to do with q, it's some field. Okay, so it's not compatible with what the original prover was able to arithmetize. The original prover worked all over secrets over fq because it only has this curve. And now we want to write operation of fp into something from fq. So it's something we don't know how to do. So there is a problem with how we arithmetize this. But maybe the solution is just to pick p and q the same, which may make everything easy here, right? But it's proven that such curves where the field, like the field over which the curve is defined and the order of the curve is the same, has discrete logarithm, which is easy to solve. So it's not a good curve that we will use for snarks. So unfortunately, we are stuck a bit. So the idea is to use 2 different curves that will lead to 2 different snarks, and we will do like a kind of a cycle between each other. So we can do this infinitely. So we start with a snark here that can prove things over fq, And the verification is FP. So secrets are over FQ, verification is operation in FP. And we need a snark that can prove things over FP, right? So we move it here and we prove the verification secret in the outer curve. And then we do this the same for the verification from the blue one in the red one and so on. So we will run in parallel two different proof systems that work on the same proof system, but on two different curves. So we can do this cycle. Unfortunately, we cannot find efficient cycles that both have pairings, unfortunately. And this means that we will need to look into systems that are not that good for the verifier runtime. So as I was saying, the ones with pairings have constant size verifier. The ones like have curves only with discrete log are linear size verifier. So we go back to the impossibility that we saw before. Linear verifier kind of leads to something that grows exponentially. And this was mentioned today multiple times. So how to overcome this linear verifier like explosion of the verifier is by doing something like, which is called accumulation. We defer the linear part of the prover to the very end. These are the two curves where we ping pong our recursion snark. And instead of running the verifier circuit, which is linear and will explode as I showed before, we rather accumulate whatever is linear into some polynomials or something that we will have to check open at the end. And we know how to open it in linear time, but we do it only once. And the rest is succinct, so everything goes correctly. Okay, so maybe I should stop here. Or, yeah.
That's an option, yeah. Yeah, it's